Everyone, welcome, and we're looking forward to this talk by George. And when he's ready, we'll just let him go ahead and get started. There you go.
All right. Well, thank you everybody for showing up. My name is George Djorgovski in real life. I'm professor of astronomy and data science at Caltech, and here you may know me as the Curious George, and I'm both of those things. So I will talk in voice. I will not pay any attention to the text chat while I'm talking. So please save your questions for after, and then precede them with capital question, colon, then ask what you want. So that way I can tell it from just a random chat. Okay. Um, so today I thought I'll tell you a little bit about stars, which are some way the basic building blocks or certainly a core subject of astronomy. And I'll tell you about how they are born, how they live, and how they die. That's shown on my title slide is one small segment of a star-forming region, so-called Carina Nebula. And this is picture taken with James Webb Space Telescope. You can see that kind of ridge-like orange stuff is really dust clouds, which are illuminated by young stars. And in the background, you see some newly formed stars. Okay, so this in a nutshell is what the life cycle of stars looks like. They're born out of these interstellar clouds of gas and dust, and usually in large numbers. They really are born when they ignite thermonuclear reactions in their core, how they produce energy, which is initially hydrogen to helium. For some stars, that's all they ever do. More massive stars make heavier elements too. And as these thermonuclear reactions evolve in time, the structure of the stars changes. And depending on their mass is how high they go in terms of heavier chemical elements. It also depends on their mass, how will they die? And that can happen in a couple different ways. For lower mass stars like our sun, eventually their core shrinks into inert ball of hot degenerate gas, which then becomes a so-called white dwarf star, and their envelope is dissipated in interstellar space, and it's called planetary nebula. More massive stars do something more spectacular. They explode, and then all of those chemical elements that they created are being ejected back to interstellar medium, where they mix with what's out there, and they form material from which new stars will form afterwards. So here is one of the iconic pictures of interstellar dust clouds with star-forming region around it. It is called Messier 16, used to be known also as the Eagle Nebula, and then the NASA propaganda machine called it the Pillars of Creation, because stars are created there, planets as well, but it is maybe a little too religious overtony for my taste. Anyway, it's a spectacular image. So what you see there are dust clouds which are illuminated by young newly formed stars, and actually this is infrared picture, so you can actually see a little bit through the dust, but it's obviously a very spectacular image. I'm sure you've seen it in the media before. Now, what are these clouds? Here is a little bit of a zoom in on a different nebula. These dark blotches are clouds of interstellar dust, and they're dark because they're pretty opaque to visible and blue and ultraviolet light. They used to be called Bok-Takeri globuli, even though they're not globulars. But those are the examples of smaller fragmented interstellar dust clouds within which stars are born. In the background of this picture is a luminous nebula with some really bright stars, which were born from the progenitor of a big cloud from which these little clouds came. And that spectacular shiny gas between the stars is mostly hydrogen with other elements thrown in, but essentially it's fluorescent light. It's like one ginormous fluorescent light bulb. And young stars excite the gas in interstellar space, and it shines out in particular emission lines, and the red one in particular is from hydrogen. So we actually do see such things happening. Now, what happens in these clouds is a very interesting little bit of physics. They're held together by gravity, self-gravity. It's big mass there, could be even as much as million solar mass, but it fragments into smaller pieces. And they're balanced against their own self-gravity, which would make them collapse by the thermal pressure, kinetic energy of atoms and ions in the cloud or dust grains. And so if they did not lose any energy, they'll probably be in an equilibrium like that. But they do lose energy because they do get hot in the middle. High potential, gravitational potential demands higher temperature. Higher temperature gas emits radiation at first in radio waves, millimeter waves, and infrared. And those photons escape from visible light. Because that energy escapes, the cloud cannot really remain its size against its own self-gravity, so it shrinks a little bit. Because it shrinks a little bit, the potential well in the middle is deeper, and so it requires more kinetic energy to balance it, which means it gets hotter in the middle. But because it gets hotter, it emits more energy. And so you have a circle of collapsing, getting hotter, emitting more radiation, collapsing some more, and eventually the cycle stops when there is a different source of energy inside the core of a forming protostar. And the different source of energy is the thermonuclear reactions. At that point, they balance the thermal energy loss from the shrinking cloud, and the whole thing stabilizes and becomes a protostar. Incidentally, the protostar has to be more massive than about 8% of the mass of our sun. If it's less massive than that, it's never dense or hot enough in the middle to ignite thermonuclear reaction. But those stars are called brown dwarfs, and they're not really stars, but they're a little more than planets. And we've known many, many of them already. Okay. So these giant molecular and dust clouds can really have masses up to million solar masses or thereabouts. And they're not stable against their own gravitational collapse and fragmenting. So they fragment into smaller subclouds about the size of typical stars. But because the whole cloud is so big, you don't make one star at a time. You make hundreds or thousands of them, sometimes even more. And when those stars ignite and their energy starts escaping from their photospheres, they clear out the gas and the dust. The dust evaporates, the gas gets pushed out, and you get things like this. You have a cluster of brand new young formed stars, and their radiation is slowly clearing out that placental cloud from which they were born. In that intermediate stage, those stars ionize the gas around them. Again, you see this beautiful fluorescent emission. Eventually, that gas is dissipated, and what's left is a young star cluster, so-called open star clusters. Those star clusters then travel around the galaxy, but they get tidally distorted and disturbed as they pass by other things, and eventually they just simply fill the disk of star form of a galaxy like the Milky Way. Oh, incidentally, really massive stars that are formed there can explode if they're really massive within millions of years as opposed to billions. And then their supernova explosions can help clear out the gas and the dust from the original cloud. Now, zooming in onto what individual protostar might look like, this is artist's conception. Pictures I've shown you so far were actual images from Webb, from Hubble, and so on. But in the middle of a star-forming cloud, material condenses in the middle, which is where it forms the protostar that then starts producing energy. But the rest of the material forms a disk around that star. And the reason it does that is that energy can be dissipated through radiation. When it's dissipated, the system shrinks. This is how you make a star. But angular momentum cannot be dissipated. So some of the material retains pretty much all of the angular momentum of the original protostellar cloud, and the lowest energy state it can have is a thin rotating disk. So this is why disks are commonplace in astronomy, whether protostellar, protoplanetary, galactic disk, accretion disks. This is the reason. Conservation laws tell us that angular momentum can be only transferred but not dissipated, and it's a much less efficient process than energy dissipation. And so you end up with a young, pressure ignited star surrounded by the disk of material, which is slowly cooling off. And we actually can observe those in millimeter waves. And well, I'll show you the picture of those in a moment. But that is the material from which planets form. So planets essentially are formed out of the leftover material from which star is made. And initially, they may be just molecules and dust grains, and then they slowly accumulate into bigger and bigger pieces, like sand, size, pebbles, rocks, boulders, eventually asteroid-sized things we call planetesimals. And more of them can then form planets and dwarf planets. So formation of planets is a common part of the star formation process. And we now believe from various measurements that there are actually more planets in the Milky Way galaxy than there are stars. There is more than one planet on average per star, and there are about 200-300 billion stars in the Milky Way alone, and then a few hundred billion galaxies in the universe. So here is the picture I just mentioned earlier. These are actual images, but not in the visible light, but in the millimeter waves obtained by the radio interferometer called ALMA, which is based in Chile, in the Atacama Desert. The colors are false colors. They're coded to intensity. But you can see that you are looking at disk-like structures with bright source in the middle. And you also notice the rings. Or rather, what you're seeing are gaps between different parts of the disk that look like rings. Those gaps are product of star formation, planet formation, because once you have a planet, massive planet, be it Earth, Jupiter, or what have you, it goes around its parent star, and it accretes the material it encounters. So it sort of vacuums up everything that's in that same orbit and grows. So planets grow, clear out their orbital path. What's not assembled into a planet yet is those leftover rings that you see. And in our solar system, there is one of those left, and that's what became the asteroid belt. But the whole picture of star and planet formation is now fairly well established and supported by observations. Okay, so what about those planetesimals? Well, some are assembled into planets, but some remain. In our solar system, those are the asteroids and comets. Asteroids are rocky ones, and they're in the inner part of the solar system. And comets are mostly composed of ice, water ice, and other light elements. And the reason for this is just mass segregation. The energy from young sun pushes out lighter elements and molecules to the outer solar system, not the rocks. Rocks are not easy to move just by radiation pressure, which is why the inner part of the solar system are rocky planets, Mercury, Venus, Earth, Mars. And in the outer parts of the solar systems, you have Jupiter, Saturn, Uranus, and Neptune. And then further out in the solar system, you have what we now call dwarf planets, Pluto, and any number of so-called Kuiper belt objects that have been discovered over the last couple of decades. We call them dwarf planets because they're small, right? But they're still planets. There was this big kerfuffle about, is Pluto a planet? Well, yes, it's a planet, but not the same kind of planet as we have the inner solar system, like Earth, or the outer solar system, like Jupiter. It's a third kind of a planet, icy dwarf planet, because you can take all of those dwarf planets in the solar system, put them all together inside the shell size of the moon. They will still rattle around and have plenty of space left. They really are small, but they're planets. Even some asteroids look like little planets. Anyway, these are the real pictures from various space missions, and some of those occasionally get kicked towards the inner solar system. That's where meteors come from. That's where asteroids that cause mass extinctions come from, or comets for that matter. And the same thing happens everywhere else in any other forming stellar or planetary system. Now, remember, stars and planets are formed in these giant clouds. It's a pretty messy situation, a lot of objects moving around. So some of these little things will get ejected from their parent planetary system due to gravitational interactions. And that creates interstellar asteroids and interstellar comets, which then as the star cluster dissipates, they too will dissipate and just float around galaxy. And sometimes some of them will come into our solar system or anywhere else. And so far we have seen 3 of those. Their first was called Oumuamua. Then and it wasn't clear it was a comet or an asteroid because it just came in too quick and people couldn't react very quickly to it. We knew such things would happen, but they're extremely rare because interstellar space is very, very big. So chances of any one of them passing through solar system at any given time are very small. But then since then, people doing sky surveys have been on the lookout, and 2 more have been found. One is called Borisov, and the third one is called Atlas. And Atlas is the one my old friend Avi Loeb went crazy about and started thinking it's interstellar spaceship, but that's a whole another story. Anyway, interstellar comets and planets are actually expected, and we have seen. All right, now let's turn to how stars, once they're formed, how they work. There are 4 important factors involved. First, they're pretty much in hydrostatic equilibrium. The gravity and the thermal pressure have to balance each other. Not absolutely exactly, which is why stars evolve. After all, they form out of equilibrium. But once they form, they can stay more or less quasi-stationary state for billions of years. Our sun has been doing this for about 4.5 billion years now, and it's got another 4 or 5 billion years to go before something changes. So that's the hydrostatic equilibrium, gravity versus pressure. The second part is thermal equilibrium, which is that as much energy as is generated inside the star has to be radiated away. And by and large, for most of the stellar life, that's the case. It's only violated really at the end of the stellar life, which is what tends to lead to stellar explosions. The third factor is how the energy was made. And I already mentioned that this is done by fusing lighter elements, starting with hydrogen, making helium, and then if there is enough density and temperature and pressure, heavier elements than that. That happens in the stellar core, which is roughly 10, 20, 30% of the stellar radius. And then that energy has to go out. But star is opaque. Stars are not transparent. I mean, that plasma that constitutes stars scatters light. And so there are 2 ways in which energy is transported from the stellar core where it's made to interstellar space, like sunlight. And those are radiation and convection. And I'll come back to those in a moment. So 4 conditions: hydrostatic equilibrium, gravity versus pressure; thermal equilibrium, how much energy you make is how much energy you have to send out; third, how energy was made through nuclear reactions; and fourth, how does it get out of the star. Those are formally encoded in so-called equations of stellar structure, which I will not show you because you don't need to know them. But when we solve those, and they're done numerically, not analytically, this is what generates stellar models, which we then use to predict how stars evolve. So I'll show you just what output of such models looks like. This is for our sun, and it shows 4 graphs: luminosity generated at the given radius as a function of the radius. 0 is the center, 1 is the surface. How much mass is contained within that radius. And on the left, those 2 diagrams, you see that pretty much all of the solar energy is generated within the central 20% of its radius, which is 20% cubed fraction of its volume. And the mass of that core, in which energy is generated, is about 30% of the entire solar mass. Stars are denser in the middle than they're on the envelope, so that's why. Typically, the density, average density in the core is hundreds of times density of water, and that's still plasma. Now, the top right is temperature as a function of radius, and you can see that in the very center it's about 16 billion degrees Kelvin, and then drops out. At the surface it's about 6,000 degrees Kelvin. And so those are the conditions in which you can actually have stable thermonuclear fusion. Tens of billions of degrees, densities of hundreds grams per cubic centimeter, and so on. Actually, what's shown on the bottom right is in kilograms per cubic meter, but you get the idea, right? So that is how we actually understand how stars work. Now, a few words about the thermonuclear reactions. Right. Atomic nuclei are composed of protons and neutrons. The number of protons tells you the atomic number: 1 for hydrogen, 2 for helium, 56 for iron, 92 for uranium. And they have comparable number of, or slightly larger number of neutrons associated with them. Now, here's the interesting thing. Mass, you take 4 nuclei of hydrogen, protons, and you make 1 nucleus of helium. But the mass of nucleus of helium is little less than the mass of 4 protons taken together. What happened is, during the reaction, some binding energy of the nucleus is released. That energy comes from the mass. And you may remember the most famous formula in physics, E equals mc squared. So the difference in mass of 4 protons versus 1 helium is approximately 0.7% of the input mass. So 0.7% of hydrogen fused into helium is turned into energy. And that's where energy of sun or other stars comes from. So it's teeny tiny amount for any one given nucleus of helium, but there is a lot of them. And so on the whole, sun makes about 600 million tons of helium every second, which sounds like a lot, and it is by terrestrial standards, but it's tiny, tiny fraction of the solar mass. Now, how does the energy get out? Okay, I mentioned the 2 ways. Radiation diffusion, and it's diffusion because the photons that come from middle of a star, which are originally just gamma rays, do not get straight out. There are also neutrinos that are made in these thermonuclear reactions. They do get straight out. About 2% of solar energy output flies out in form of neutrinos, and all of us are being passed through by this neutrino wind that comes from sun. And neutrinos mercifully do not interact very well with other particles, but we can detect them, special detectors. And so at any given time, hundreds or thousands of neutrinos are flying through your body at nearly the speed of light, not quite. Now, the photons will then encounter atoms and nuclei, etc., and will get broken into smaller energy photons, and slowly but surely the energy will diffuse out. I'll show you that in a second. But if the plasma is too opaque, then radiation is not a very effective way to get it out. And that's where convection comes in. Convection is basically boiling. When you're boiling pot of water on a stove, the input of energy from your hot stove is so high that it's very hard for water to just radiate it away, and that's where it starts bubbling and boiling. Well, same thing happens in stars. Stars are boiling inside, not throughout, some in the middle, some on the out envelopes, and it depends exactly on the number of factors, but that is how energy gets out. Now, thermal diffusion. All right, so you have high energy photons, which then hit other particles, heat them up, they emit more photons. Those photons then go in any odd direction, not just in radius. And long story short, it takes about 250,000 years for energy made in the solar core to actually emerge in the solar photosphere. So if sun were to somehow turn off its energy production right now, we will not know about it for another 250,000 years. Now, sun's not going to do that because there are really good reasons to believe why it wouldn't. But someday it does. This is when stars end their lives. Okay, so again, if plasma that makes bulk of the star, all of the star basically, is too opaque for light of any given frequency or wavelength to pass through, convection becomes a more useful way or a more effective way to get this energy out. Because remember, as much energy as you make in, that's how much energy you have to radiate away at the surface. Now, how much of what depends on two things. Depends on mass of the star and depends on its evolutionary stage. For a very massive star, during most of its lifetime, the core is so opaque that it's convective, and bulk of the envelope is radiative. The lower or intermediate mass star like Sun has radiative core and most of the volume, but a very convective envelope. And a very low mass star is entirely convective, because they're too cold. Colder plasma is more opaque, and therefore convection is by far the most preferred way of moving energy out. Well, what happens with stars where do have convection in the outer layers? That causes stellar activity. Here are pictures of the sun in visible light, in ultraviolet and X-rays. And you can see there are all these bright spots, there are solar flares, there are dark spots, those are sunspots. There are these things called prominences and protuberances, because in addition to the energy, there are magnetic fields inside the sun, and they're kind of tied together with plasma. Plasma is essentially electricity, but well mixed, positive, negative, and magnetic field tends to be frozen in such a material. But nevertheless, as it moves out, those magnetic fields also move out. They trap the plasma, and then you can get things like the one shown on the left, prominences that look a little bit like magnetic fields of force. That's not an accident. And since they're being pushed out by energy transfer, they go off into the interplanetary space, and those are called coronal mass ejections. So that's what generates solar wind, and all stars do that. Solar wind then sends energy and magnetic fields out into its planetary system. When one of those hits the Earth, and they do all the time, that's what causes, well, things like polar lights, which look pretty, that's where the energy goes. But also the magnetic fields mess up with Earth's magnetic field and cause what we call geomagnetic storms. Now, Earth's magnetic field is a really important thing, not just for navigation, but it protects us from most of the energetic particles that come from the sun, solar wind. If it wasn't for solar wind, we'll all be dead from skin cancer a long time ago. So if you mess up with Earth's magnetic field, yeah, you can create a lot of trouble. And sometimes there are these gigantic solar activity events which can really mess up things. There was one in UK, forget, over 100 years ago, but they do happen. And because we're talking about magnetic fields and electricity, they can mess up power grid. They can mess up with any electronics you may have. If a really big one happens now, it will fry all of our satellites, including all of the GPS, all of the satellite-based communications. Any astronauts in the orbit will have a really bad day. And it does happen, but the big ones don't happen all that often. So this, in fact, may be one of the factors which determine whether or not life develops and survives on planets around stars that are convective in the outer regions. One of my colleagues, Greg Hallin, has been working on that. And the low mass stars, which are highly convective, can have phenomenal flares. Solar flare might increase solar brightness by 0.1%. For these dwarf stars, star can become hundreds of times brighter in a matter of minutes and then comes down. But those are pretty damn big flares. Okay. So how do astronomers study all this? An extremely useful tool for this is so-called Hertzsprung-Russell diagram. And because people can't spell Hertzsprung, I sympathize with that. It's called HR diagram. And it's plot of luminosity of a star versus its surface temperature. It turns out stars do not fill up this diagram randomly, but they really line up on these one-dimensional sequences. And most of them sit on the sequence that's in the lower right. It looks fat because of the measurement errors, but it's almost completely thin. That's where stars land when they form, and that's where they spend most of their lifetime. This is where they're converting hydrogen into helium in their core. Once they can no longer burn hydrogen into helium, they start burning hydrogen in a shell around the helium core, and their structure changes. They puff up. They become so-called red giants and ascend what we call the red giant branch. Now, if they're not very massive, like Sun, at some point, they'll just stop making energy, dissipate the envelope, the core becomes white dwarf, envelope becomes binary nebula. If they aren't sufficiently massive, then they will ignite helium burning into carbon and move to the thing on the left called the horizontal branch, and so on. So more massive stars do more interesting paths on this diagram, and we can compare that with observations and use that to constrain our stellar evolutionary models. But bulk of the stellar lifetime is spent on the so-called main sequence, and every subsequent stage lasts less because thermonuclear reactions that define that sequence go faster and faster and faster. And I'll give you an example of that in a bit. Okay, so what happens with a star like Sun? Okay. When it fills up its core with helium, there is no more hydrogen to burn in the core. So core doesn't generate energy. And hydrogen still burns in a thin shell around that helium core. But that then changes things. And as I said, the envelope puffs up, becomes more opaque, expands, becomes very convective. And so for lower mass stars, that's pretty much all there is. For more massive stars, you can then have ignition of helium, carbon, and higher elements. And this is a process that we understand fairly well altogether. The most massive stars drive the most significant stellar winds. There is so much energy coming out of them that they essentially blow their envelopes away slowly, and then in the end explode. So these pictures are so-called planetary nebulae. They're called that way because back in the olden days, before we knew any of this stuff, people were looking for planets after Uranus and Neptune were found. That was a big thing to do. And in the old telescopes, these fuzzy little things look like disks, and that's exactly how gas giant planets look like through those old telescopes. And so they were misnamed planetary nebulae, have nothing to do with planets. Those are the envelopes of low-mass stars undergoing their final life stages. And they can have a variety of structures, and it all depends on exactly how a star was in the envelopes, what was its rotation, what it was wind, and so on and so forth. The one that is middle row, third one from the left, is so-called ring nebula. And you will notice in some of these pictures, there is a little bright dot in the middle, and that's the leftover incandescent but inert core that then becomes a white dwarf star. White dwarf stars do not produce energy. They just radiate away the accumulated latent heat that was in them, because they start with like billions degrees of Kelvin temperature and eventually cool down. They have a mass of, say, solar mass, from 2/10 of solar masses to 1.4 times solar mass, and all that squeezed down in a volume equal to the planet Earth. So their gravity is very, very strong, but they still do not produce energy. They just shine it away. And they can last billions of years. And in principle, eventually they can get so cold they crystallize. The whole star can become a solid body. We've never seen this because it takes many billions of years to happen, but if you just follow thermodynamics, it will. Okay, now what about more massive stars? More massive stars will first burn hydrogen into helium in their core. When they cannot do that anymore, there will be helium in the core, hydrogen burning a shell. Eventually, helium ignites and starts making carbon in the core, and so on and so forth. And that goes on and on and on, depending on the mass of the star, until eventually, for the most massive star, you have this kind of onion shell structure. You have iron core, which does not burn, surrounded by the shell of silicon that burns, creates iron, etc., carbon, and so on, oxygen, helium, and the outermost envelope of star tends to be hydrogen. Now, why iron? What's so magic about iron? Well, remember, I told you that if you have light elements like hydrogen burning to helium, the mass of the product is less than the mass of the input components, and that is the energy that gets to be radiated away. So for the lighter elements, combining them into heavier elements produces energy. By far the most of it hydrogen to helium, but with every subsequent stage still makes some energy, less and less, until you get to iron. Heavier than iron, the opposite happens. The more massive nuclei generate energy if you break them into smaller ones. And the apex of that curve is iron. It's the most stable one of those. But this is why the atomic energy, fission energy, uses heaviest elements they can, like uranium or plutonium, because that's how you get most of the atomic energy, by breaking those nuclei into smaller ones, and that's where nuclear reactors and atomic bombs come from. On the other end, low mass end, that's where hydrogen bombs come from, fusing hydrogen into helium. But anyway, iron is for complex reasons, the peak of stability, and it cannot burn anymore in any quasi-stationary process like that. Now, I mentioned that subsequent stages of this thermonuclear evolution are faster and faster. So what's shown here in the table is temperatures and densities of stellar cores for given fusion reaction and how long that can last. And this is for like a very massive star. So for a very massive star, hydrogen burns into helium for 40 million years, say. For about 7 million years. That's the most massive stars. For Sun, it's almost 10 billion years. Then for helium, burning into carbon, it's an order of magnitude less. And then carbon into neon and oxygen and so on and so forth goes faster and faster and faster. Silicon burning into iron takes a day, after which star will explode, because it will take a quarter of a second for that to happen, and then the supernova explosion happens. So stellar evolution is essentially a sequence of thermonuclear reactions in the stellar core, and the heavier you go, the faster it happens. And in the end, it ends with a nice explosion. So this is what happens. You have eventually inert iron core. It's not producing any energy, and therefore there is nothing to hold it against its own self-gravity, and the core starts to collapse. As it collapsed, iron is broken apart into protons and neutrons, and protons and electrons combine to make neutrons, creating neutrinos and extra energy. And basically, that iron core transforms itself, most of it, into pure neutron material. But that shock then that creates involved shock that then reverses and starts pushing material out. And it's that outward going shock that is in part driven by neutrinos that are captured with so incredibly dense material that happens here. That's what explodes the star. So there is innermost core, which did not explode, which collapses into one of the two outcomes about to talk about, and most of the star is just blown apart by this explosion. And that's what happens in supernova explosions. Like this. This, of course, is the Crab Nebula, supernova observed in 1054, everywhere in the world. It's famously been noted in China by Chinese astronomers, but everywhere else, like in Native Americans, in Chaco Canyon, and so on and so forth. For a long time, there was puzzle why there was no mention of it in the European records of the time. And that's not quite true. Some records have been found in obscure monastery chronicles and stuff like that. But there was an interesting possible explanation, because supernova was visible by naked eye, even during the daytime. And that just didn't fit well with church dogma of the skies being unchangeable and perfect and God created. And you can't have suddenly, a really new star. And since that didn't quite fit in the prevailing dogma, people didn't want to write it down. So there was a scene in one of the books, I forget which one, in which an astronomer talks about this in a planetarium and says something to the effect, the dark age is a cold dark, not because the light fails to shine, but because people refuse to see it. Anyway. Two possible outcomes of this are neutron stars or black holes, ever popular black holes. So remember that iron core has been all broken up by the gamma rays and whatnot, and essentially turned into pure neutronium, if you will. So for stars that are typically in range of between 8 to 25 solar masses, that's the outcome. You make a neutron star, which is typically 2 or 3 solar masses, but 1.4 solar mass is an interesting number, and that a lot of them end up in that. Less massive than 1.4 solar masses are not neutron stars, they're white dwarfs, that I mentioned earlier. But now this material, which could be more massive than the sun, twice massive than the sun, is compressed into a ball of neutrons that's about 10 kilometers in size. So it's typical size of a small city or town, like Pasadena, for example. And it has 1 or 2 solar masses worth of stuff. So that's pretty dense. It's like one ginormous atomic nucleus. They have structure, but never mind. They also inherit angular momentum of the core, stellar core, which collapse to make them. And because they shrink, they start spinning fast. You may recall from your elementary physics, like when a figure skater, when they bring their arms close, then they start spinning faster because angular momentum is conserved, and it depends on the radius and so on. And they also inherit all of the magnetic fields of the plasma in the core. So you have a ball of neutron material, density that's 15 orders of magnitude larger than, say, density of water. And it's a pretty extreme object. You start seeing relativistic effects and all other kinds of stuff. So let me just give you a little bit of history. What about this? Neutrons as particles were discovered in 1932. And 2 years later, already astronomers like Walter Baade and Fritz Zwicky at Caltech speculated that that is exactly what can explain supernova explosions, because they've studied supernovae. They figured out supernovae are something that's much more dramatic than ordinary novae, which are just highly variable eruptive stars. And they did speculate correctly that a supernova produces a neutron star. They didn't know about black holes quite yet. So that was more or less accepted for a while, but there was no direct evidence for neutron stars until 1960s, when radio astronomy really began. And radio astronomer Anthony Hewish had a brilliant young student, Jocelyn Bell, and they were looking really at interplanetary scintillations. And Jocelyn found sources on radio sky that appeared as periodically spaced pulses with periods of some milliseconds or tens of milliseconds. That was surprising, because up until then, nothing in astronomy was changing that fast, because it takes time for big things to change. And so it did imply that we're talking about something small and so on. At first, they thought maybe these are signals of extraterrestrial intelligence sending us one dot Morse code. But they quickly figure out, no, it's not. It's the neutron stars, because they're small enough to spin at periods compared to what's observed. Notoriously, Hewish and another radio astronomer, they're real pioneers of radio astronomy, got Nobel Prize. Jocelyn, who actually found the pulses, didn't. But she got celebrated quite extensively later on, and she won one of those breakthrough prizes. Nobel Prize, which these two guys shared, is only $1 million. Jocelyn got $3 million breakthrough prize. I had fortune to meet her. She's a very, very nice person, very friendly, and not at all vain about her achievement. Back then, they were using chart recorders, like the strip that I was showing you down there. Since then, pulsars became a big industry. There are now different kinds. The fastest ones spin at about a millisecond, and so on. Well, okay, what do they do? Remember, I told you they spin fast because they inherited angular momentum of stellar core. They also have strong magnetic field because they inherited that too. Magnetic fields accelerate charged particles. This is how all particle accelerators work. So essentially, they have a jet of fast particles emerging along their magnetic poles, which are not the same thing as their axis of rotations pole. And so they just sweep the sky with these beams of particles, which radiate in radio waves and X-rays and so on. And that appears like a lighthouse. If you're in the path of that beam, we'll see a pulse, and we'll see it with the uniform spacing, because they're so dense, the moment of inertia is so high, stability of these rotating beacons is extremely, extremely strong. They do change occasionally, and that's a whole other story. But essentially, pulsars form the most precise clocks known to us, because they're so massive, spin so fast, and last for a long time. They're used for a variety of other things, but we'll leave it at that. Now, what happens if the core is so massive that even pressure of neutrons cannot hold it against its own gravity? Then it undergoes gravitational collapse, and this was first figured out by Oppenheimer of the atomic bomb fame and his collaborator, what's it called? I forget his name. And they first solved exactly mathematically using theory of relativity equations what's going to happen. So you end up with some big chunk of mass of the core falling together until its density or surface gravity, so to speak, is so high that not even light can escape. And that's what we call a black hole. But it's not so simple as that. The gravity is so strong that it changes the geometry of space-time. You may have heard that general theory of relativity says that presence of mass or energy changes the geometry of space and time, changes the curvature. Black hole is like the extreme example of that. This has been really well established. So, well, how can you think about this? Here is an intuitive but really incorrect explanation, and you can think of it in Newtonian terms, right? You have some object with a mass m, little m, and it is from surface of the mass big M, which has a radius r. So it has its potential energy due to gravity, and if you give it some kinetic energy, and formula is mass times velocity squared divided by 2, and for potential energy is Newton's constant, the product of two masses divided by the radius. If the kinetic energy is bigger than potential energy, it's going to fly away. So for Earth, that escape velocity is 11.2 kilometers per second. Now, you can see that it depends on both mass and radius. So you have two ways to increase this escape velocity. One is add more mass within the same radius. The other one is keep the same mass but make it smaller. So what happens in gravitational collapse? Mass is still there, but the radius shrinks. If it shrinks sufficiently so that this escape velocity is greater than the speed of light, then not even light can escape, nothing can escape. So things can fall in, but nothing can get out. And that is what we call black hole. And the surface of that radius at which escape speed becomes speed of light is what we call the event horizon. This is only very loose Newtonian analogy, what's really happening, but I think you kind of get the idea. Now, black holes are fascinating, and maybe one day I'll give you a talk about black holes alone. But for now, we're just going to move on. And so if they're black, if they don't shine light, how can we find them? Well, there are different ways. First of all, we never see a black hole by itself. But if it's in a binary star, and a lot of stars are in binaries, we used to say like 3 out of every 2 stars are in binaries. Well, if one of them is a black hole, becomes black hole, and the other one is not yet, the black hole will suck up all the material from the normal star. That material will fall in, but remember, angular momentum is not dissipated. So some of it will fall in black hole. A lot of it will be settled into a little thin spinning disk around the black hole, from which it will dribble and dribble into the black hole. And that's called the accretion disk. So as the material comes in, hits the disk, heats it up, that disk gets to be really, really luminous. And that can happen with pairs of black hole and a normal star. It also happens with neutron star and normal star and so on. But in centers of galaxies, we have gigantic black holes that can be billion times the solar mass. They're not made from stellar explosions, at least seeds might be, but not the whole thing. And they can outshine the entire galaxy by factors of thousands from just the accretion into a disk. So just going back to the stellar origin black holes, we've seen hundreds of them through this process. If we follow the stellar evolution, we know how many stars are made per unit time, how many are massive, etc., etc. We estimate there are currently about 100 million black holes from massive stars in our Milky Way galaxy alone. That sounds like a lot, but Milky Way galaxy has a couple of 100 billion stars, so 100 million black holes is not so bad. And there are now new ways actually finding them through their effect on other objects nearby or even gravitational lensing. So that's how you can detect presence of black holes in visible light, but never see actual black hole. As one of my old professors used to say, I'll believe in black holes when I see one. Well, he was a little too conservative about that. The new way of doing this is you can see them through gravitational waves, so to speak. Black holes are essentially gravity sources, huge gravity sources. Now, if it's just sitting there by itself, that doesn't help you much. It can be detected to gravitational lensing of objects behind it. But just as stars can come in binaries, well, sometimes some binary stars can, both components are massive enough to make a black hole. And you end up with a binary black hole. That's the end product of the evolution of the two progenitor stars. They'll spin around common axis, but they'll start losing energy. Even though they don't radiate any light, they still radiate gravitational waves. Because they're losing energy to gravitational waves, the orbit shrinks and shrinks and shrinks, and eventually two black holes merge. The gravitational waves that they emit up until that moment are pretty low intensity, but as they approach the merger and merge, you see a burst of gravitational waves, which we now can detect with interferometers like LIGO and so on, and that resulted in a Nobel Prize a few years back, deservedly so. So now we can actually observe the sky not just in electromagnetic radiation, but in gravitational waves as well. And that has resulted in all manner of very exciting, interesting science. So we can actually kind of see black holes. Now here is a diagram that people who detect gravitational waves made. It's called masses in stellar graveyard. What's shown here are, there are always three dots in a vertical line. The two lower dots are the masses of the two objects that merge, and the top one is the mass of the object that was generated by the merger. The blue ones are for black holes, the yellow ones are for neutron stars. That is another interesting story, but let's just focus on the black holes. The scale on the left tells you the masses in solar mass units. And if you squint and see that, we're talking about tens of solar masses in black holes. Now, when two black holes merge, they lose about 10% or so of the initial mass of the two black holes to gravitational waves. And that is a lot of energy. This is why we can actually detect these gravitational wave bursts. So that's part of so-called multi-messenger astronomy. Astronomy used to be all about electromagnetic waves, light, radio, X-rays, whatever. But now we also have gravity waves. We also observe high-energy particles and neutrinos, and all that kind of combines to give us a much better picture of what physical universe is like. All right, so what happened with the envelope of that exploding star? Core becomes neutron star or black hole, but bulk of the mass of the star is now exploded and sent into the interstellar space. And that's where all those chemical elements that have been cooked up in stellar interior, and some of them during the explosion itself, are being sent out to interstellar space and mixed with all of the material that's already there. And new stars will then be made from that newly chemically enriched material, which is why we talk about life cycles of stars. So this is essentially the summary of it. right? You have interstellar clouds. They collapse, they make stars, low mass stars, burn hydrogen to helium. Eventually, they just stop making energy. The core becomes white dwarf, size of planet Earth, passively cooling, envelope becomes beautiful planetary nebula, dissipates in interstellar space. More massive star undergoes a series of thermonuclear reactions all the way up to iron, explodes, makes either a neutron star or a black hole, and most of the stellar mass then gets sent back to the interstellar medium, now chemically enriched. So you have this cosmic ecosystem of gas, stars, energy, and chemical enrichment. And that's essentially what leads to galaxy evolution itself, from stellar evolution into the galaxy evolution. All right, I believe that this is all I have. Let me just make sure. Yes, and it's 11 o'clock. I'll be happy to answer a few questions because we don't want to have Ari waiting for us in Scientia Music Pavilion, but please feel free to reach out to me and ask any questions you may have. So, Stephen, let's take a couple questions and then dissipate into the intersecond life space. Okay, here we go. Question. Please explain why photons supposedly only take 200,000 years to reach the solar surface, and yet the Kelvin-Helmholtz timescale is about 20 million years. What timescale is the cooling time in the sun's nuclear reaction? Turn it off. Okay, good question. I did not mention Kelvin-Helmholtz timescale because before we knew that stars make their energy in thermonuclear reactions, the only thing people could think of is that, well, they have a binding energy and they're shrinking, and shrinking makes them hot, and that heat, which is exactly what happens with protostars, is the source of stellar luminosity. Well, it wasn't the case, because if you do that, stars can only last some millions of years, whereas already with, Rutherford and so on, we knew that there are rocks that are billions of years old through radioactive dating. And so it became very clear by 1930s that it's not just this radiation of binding energy, but there is a genuine new energy created through thermonuclear reactions. Now, the question of timescales is, well, that so-called Kelvin-Helmholtz mechanism, if you just start with the mass of the sun and let it shrink and radiate the energy away, that does end up being something like tens of millions of years. As far as I know, that is not taking into account anything about efficiency of radiation or opacity or any of that. In fact, protostars collapse exactly at Kelvin-Helmholtz timescale because that radiation escapes from protostar because it's sufficiently long wavelength. It doesn't care about dust. But yeah, if somebody were to actually bother to do proper computation, that too will take longer for the same reason. By the way, Jupiter is doing exactly that. Jupiter is still slightly shrinking, and Jupiter is emitting more radiation than what it receives from the sun. So, okay, let me just see. No other questions. Everything was crystal clear. Wonderful. Okay, well, please join us at Scientia with Maestro Ari playing piano in our music pavilion. And again, reach out to me whenever you want if you have any questions about any of this stuff. So thank you all for coming again.